Welcome to this session on Switching Vector Autoregression Analysis, a crucial part of our Advanced Time Series Analysis course. We will be delving into both the theoretical underpinnings and practical applications, specifically demonstrating how to implement these models using EViews versions 13 and 14. This module is brought to you by the Vietlod Econometrics Group. As the excerpt on the slide highlights, integrating individual series and accounting for concepts like equilibrium error naturally leads us to more sophisticated modeling frameworks, such as vector error correction models, and, by extension, the switching VAR models we'll explore today. These advanced models are essential for capturing the dynamic, nonlinear behaviors often observed in economic and financial time series, moving beyond the limitations of traditional linear models. The fundamental problem with a standard VAR model is its assumption of linearity and stability. It presumes that the parameters governing the economic system are constant over time. However, the real world is not so simple. Economies experience structural breaks due to events like wars, major policy shocks, or financial crises. They also shift between discrete states, such as a recessionary period versus an expansionary one. When a linear model is forced upon data that contains these different regimes, it essentially averages them out. This leads to a poor fit and, more importantly, unreliable forecasts. Think of modeling traffic speed. A single average speed for a 24-hour period is useless. You need at least two states: rush hour, slow, and off-peak, fast. A linear model gives you the useless average, while a switching model can identify and analyze the two distinct states. Given these limitations, how do we decide which model is appropriate for our multivariate time series data? Let's look at a decision map. When you have multivariate time series data, the first question is about stationarity. If variables are non-stationary and co-integrated, a VECM is appropriate. If the variables are stationary, we then ask if the parameters are constant. If yes, a standard VAR model is sufficient. If the parameters are not constant, the final question is about the nature of the change. If the parameters change continuously and slowly, a time-varying parameter VAR is the right choice. But if the economy jumps discretely between a few specific states, like high versus low volatility, then the switching VAR is the superior method. Switching can be driven by an observable threshold. This is simple switching. For example, the model switches to regime A whenever inflation exceeds 2%. More commonly, the state is unobserved or latent. We don't know for sure if we are in a recession. We can only infer it. This is where Markov switching comes in. The probability of being in a certain state today depends only on the state we were in yesterday. This is the essence of the Markov property. The future is conditionally independent of the past, given the present state. The model doesn't need the entire history of the data, just the most recent state, to predict the next one. Think of weather. A simple switching model might be, if temperature is below freezing, use the snow model. A Markov switching model is more like, if it was sunny yesterday, state 1, there is a 90% chance it will be sunny today. If it was rainy yesterday, state 2, there is a 60% chance it will be rainy today. The state is probabilistic and depends on the previous day's state. This concept of a probabilistic, unobserved state is central to the model. Let's formalize this in a mathematical framework. Here is the general form of a switching VAR model. YT is a vector of our endogenous variables. The model's parameters, specifically the intercept, mu, and the coefficient matrix A, are dependent on the state, ST. This state variable ST is discrete, taking values from 1 to k, where k is the number of regimes. The error term, epsilon t, is assumed to be normally distributed with a mean of 0 and a covariance matrix sigma, which can also be state-dependent. EViews offers two main specifications. In MSI, Markov switching intercept, only the intercept term mu sub st switches. In MSM, Markov switching mean, the overall mean of the series switches. While mathematically similar, they result in different dynamic responses to shocks. First is identifiability. The model must be able to statistically distinguish between the regimes.
If the parameters for regime 1 and regime 2 are nearly identical, the estimation will fail because the model can't tell them apart. Second is ergodicity. The system must not get permanently stuck in one state. There must always be a non-zero probability of transitioning to any other state. This ensures the process is stationary in the long run. Third, while the overall series might not be stationary, the variables should generally be stationary within each regime. Finally, a practical condition is the number of regimes. While theoretically you can have many, in practice, models are usually limited to 2 or 3. Adding more regimes causes the number of parameters to explode, leading to computational issues and convergence failures. As a pro tip, start with 2 regimes. Increasing to 3 or more causes the number of estimated parameters to explode, often leading to convergence failures. For identifiability, imagine trying to distinguish between a slow growth regime and a very slow growth regime. If the data doesn't clearly separate these two phases, the model will struggle to estimate the parameters for each, and the results will be unreliable. Once we've estimated a model that meets these conditions, a key piece of output is the transition matrix, which tells us how sticky or persistent each regime is. The transition matrix, denoted by P, contains the probabilities of moving between states. The diagonal elements, Pii, are particularly important. They represent the probability of staying in the same state. A high Pii means the regime is very persistent or sticky. We can quantify this persistence using the expected duration formula, which is simply 1 over 1 minus Pii. This tells us, on average, how many periods the system will spend in a regime once it enters it. For instance, if the probability of staying in a recession, regime 1, P11, is 0.95, the expected duration of that recession is 1 over 1 minus 0.95, which equals 20 periods. This provides powerful economic intuition. If an economy enters a high growth regime and the transition probability of staying there is P22 equals 0.90, the expected duration of the boom is 1 over 1 minus 0.90 equals 10 quarters. This is a tangible forecast about the stability of the current economic phase. Understanding the persistence of these states is one thing, but how do we actually estimate this model in practice? Let's turn to EViews.
Let's walk through the steps in EViews. First, you need to have your work file open with your time series data. The standard way is to navigate through the menus. Click on Quick in the main menu, and then select Estimate VAR from the dropdown. This will open the VAR specification dialog box. Here, the crucial step is to change the VAR type from the default to Switching VAR. For power users, you can simply type VAR in the command line and hit Enter to bring up this dialog directly. The Basics tab is where you define the core structure of your VAR model, just like you would for a standard VAR. In the Endogenous Variables box, you'll list the variables you want to include in your system. For example, GDP growth, inflation. In the lag intervals box, you specify the lag structure. For example, 1-2 tells EViews to include the first and second lags of the endogenous variables as regressors. A key tip here is that lag selection is critical. While switching VARs are powerful, they have many parameters. Using too many lags can quickly exhaust your degrees of freedom. It's often a good idea to run a standard VAR first and use information criteria like AIC or BIC to guide your lag choice. This tab is the heart of the setup. First, ensure the switching type is set to Markov. Next, specify the number of regimes. As we discussed, it's best to start with 2. Finally, you must choose which coefficients are regime-specific. This is a critical choice. Letting all coefficients switch, including the lag coefficients, can make the model extremely difficult to estimate and prone to instability. A robust starting point is to only allow the intercept/constant and the error variance to switch between regimes. This allows the average growth rate and volatility to change, which often captures the most important dynamics. For our case study, we'll use data on GDP growth for 4 G7 countries: Canada, Germany, Japan, and the US. The data is from the OECD national accounts.
The central goal is to see if the model can, on its own, identify distinct global economic regimes from this multivariate data. Specifically, can we find a recession regime and a growth regime without pre-specifying the dates of recessions? We want the model to learn these hidden states purely from the co-movement of the G7 economies. Looking at the chart, you can visually see periods where all countries dip together, like around 1975, the early 1980s, and 2008. The goal is to have the switching VAR model formally identify these periods as a single recurring recession state. Let's specify the exact model we will estimate for this case study.
The model we'll estimate is a Markov switching intercept VAR, or an MSI VAR2. The endogenous variables are the GDP growth rates for the 4 G7 countries: DP Can, DP DAU, DP Japan, and DP USA. We are using a Markov switching type with 2 regimes and 2 lags. Crucially, we are only allowing the constant, the intercept, to switch between regimes. For simplicity in this example, we are keeping the error variance common across both regimes. This specification allows the average growth rate to jump between regimes, while assuming volatility remains constant. A key technical detail for estimation is to set a very precise convergence tolerance, like 1e to the 8th. Switching models require this precise optimization to distinguish between subtle regime changes and ensure accurate identification of the hidden states. The output will provide separate coefficient estimates for each regime. Here, we focus on the constant or intercept term. In our hypothetical results, regime 1 has a negative constant of negative 0.05, while regime 2 has a positive constant of positive 0.80. This is a successful result. The model has identified 2 distinct states, one associated with negative average growth, a bust or recession, and one associated with positive average growth, a boom or expansion. It learned this distinction directly from the data. To formally check if the switching model is an improvement, you should compare its log likelihood value to that of a standard linear VAR. A significantly higher log likelihood for the switching model indicates a better fit. After estimation, you can plot the probability of being in a particular regime at each point in time. In EViews, this is found under View, Regime Results, Regime Probabilities. This chart shows the smoothed probability of being in regime 1, which we've identified as the recession regime. The gray bars represent official NBER recession dates for the US. As you can see, the model does an excellent job. The probability of being in the recession regime spikes to nearly 1 during the periods that correspond to official recessions. This is a powerful visual validation of the model's performance. It's important to use smoothed probabilities for historical analysis, as they use all the information in the entire dataset to estimate the probability of being in a state at any given time, t. Filtered probabilities, in contrast, only use data up to time t, making them suitable for real-time forecasting exercises. The peak around 2008 on the chart shows the model is almost 100% certain that the G7 economies were in the recession regime during the global financial crisis, aligning perfectly with our knowledge of economic history. This plot tells us when the regimes occurred. To understand how persistent they are, we need to examine the transition matrix. This slide presents the crucial transition matrix and the derived expected duration for our identified economic regimes. The transition matrix shows the probability of moving between states. Here, the value 0.75 on the diagonal for regime 1 means that if the economy is in a recession this quarter, there is a 75% chance it will remain in a recession next quarter. Similarly, for regime 2, which we identified as the growth phase, the 0.90 probability indicates a 90% chance of staying in growth if currently in it. Using the formula 1 divided by 1 minus the probability of staying in a regime, we calculate the expected duration. For regime 1, the recession phase, the expected duration is 1 divided by 1 minus 0.75, which equals 4 quarters, or 1 year.
For the growth phase, regime 2, the expected duration is 1 divided by 1 minus 0.90, which is 10 quarters, or 2.5 years. These probabilities are incredibly important for forecasting. For instance, if we determine the economy is currently in a growth phase, this matrix tells us there is a high 90% chance it will remain in that growth phase next quarter. This provides valuable insight into the persistence and dynamics of our economic cycles.
A major advantage of switching VARs is the ability to compute regime-dependent impulse response functions, or IRFs. A linear VAR produces only one IRF, assuming the response to a shock is the same regardless of the state of the economy. This is often unrealistic. Switching VARs, however, produce multiple IRFs, one for each regime. This allows for a much richer policy analysis by showing how the economy responds to the same shock under different conditions. For example, the chart on the left illustrates the response of U.S. GDP to a shock during a recession, regime 1, showing a deep and prolonged downturn. In contrast, the chart on the right depicts the response to the same shock during a growth period, regime 2, where the dip is much milder and shorter-lived. This vividly demonstrates that shocks are not symmetric. Their impact critically depends on the state of the economy. A policy shock, for instance, might be highly effective in a boom, but could fail in a bust, and switching VARs are crucial for capturing this asymmetry in economic responses. To recap, we've seen that linear VARs fail to capture structural breaks. Switching VARs allow parameters to change based on latent regimes. EViews provides a robust GUI for Markov switching estimation. Our analysis relies on interpreting regime probabilities and transition matrices to understand the dynamics. For quick EViews commands, use VAR to start and view regime results to see the identified states. Ultimately, models are approximations, but switching models